If I have a curve given parametrically, what is this arc length? Now the equation that I have up right now is the familiar equation for arc length when my curve is described as the graph of some function, where I've got a y that is a function of x, and we have this particular expression for it. But what I want to do is note that if I make the change where x is some function of t, and then y is some function of t, we've previously seen that the derivative of dy dx could be written as dy dt all divided by dx dt. This was a consequence of the chain rule. So let me come and take this thing and put it in for my dy dx. And while I'm making the change from x's to t's, I'm also going to note that my integral needs to change from an alpha to a beta, just as it did before, when I have that x of alpha is equal to a and x of beta is equal to b. So square root, that part stays the same, the one that starts the same, but I do have the dy dt all divided by dx dt. That is in squared and all inside of the square root. Now, last thing I have to change is the dx, because I'm trying to change from an integral with respect to x to an integral with respect to y. I'm trying to make that substitution. So my substitution rule tells me that my dx is going to go to dx dt multiplied by dt. So I'm going to put on the outside a dx dt multiplied by dt. So that is the replacement of the little dx. And then if I have a dx dt on the outside of the square root, if I want to bring it inside of the square root, what I get is the following. The integral from a up to b of square root of, and I'm going to bring this up over here, dx dt squared. I have it as squared because I'm taking something that is not squared and putting it inside of a square root. And then the dx dt on the denominator gets cancelled, and I'm just left with dy dt. And all of this dt. And so we've derived a formula for the arc length of a curve if my curve is defined parametrically. So here's a very standard question, a question that we should know the answer to. What is the arc length of a semicircle? And indeed, we have a very familiar formula, 2 pi r, for the circumference. Circumference is another way of saying arc length in the particular context of a circle. We know what the circumference of a circle is, and therefore we know what the arc length of a semicircle is. But let's see if we can derive it. Now, previously, before we started dealing parametrically, if I wanted to try to describe a circle or a semicircle, we might have tried to have y is the square root of 1 plus x squared. We would have used our familiar arc length formula. It would be some messy thing, and maybe it would work out to some nice value. But I want to see how we can do this parametrically. So if I use the standard parameterization for the circle, it tells me that x of t, of my parameter, is just 1, if it's a circle of radius 1 times cosine of t. And that my y coordinate as a function of t is given by sine of t. And in particular, if I only care about a semicircle, perhaps I'll do this one that looks like that. And I can make a restriction on my domain. I'm going to have 0 up to t up to pi. If I wanted to go from pi to 2 pi, that would do the portion underneath the x-axis. But this is going to be sufficient for just a semicircle. Now, arc length was given by our formula. So let's try to put in all the different components of it. So first of all, I have to give the t value at the start and the t value at the end. So this is 0 up to pi. Next up, square root. And then I have to put in the derivative of x squared. So derivative of x, derivative of cosine is minus sine. That's squared, the minus sign goes away. And it's just going to be sine squared of t. And then derivative of y with respect to t, so this derivative of sine, which is cosine, I'm going to get a cosine squared of t, and then all of this dt. Now, sine squared plus cos squared is 1, so this is the same thing as the integral from 0 up to pi dt, and then that is just going to be equal to the value of pi. Does this make any sense? Well, indeed, the circumference of a circle of radius 1 is 2 pi r, so 2 pi times 1, just 2 pi, and then a semicircle is half that, so pi. So indeed, we have pretty effortlessly figured out this interesting and important fact by our ability to compute arc length of parametric curves.